On the first day of class, I told you one of the benefits of this class is that the units are kind of independent of each other. So if you did not love systems of numeration and the Mayan system and different bases, then the good news is you won't see that again until the final exam review. Okay, so we're going to start something completely new and different. I enjoy this section, this unit, simply because I think it gives you a little more idea of the breadth of mathematics, how kind of wide the topics are. So it's kind of interesting. So this first section, as with most of them as we go through, is going to be concerned with some terminology that we have about something brand new. And then we're going to get to have some fun with them, the stuff that we talk about on Wednesday and when we come back next week. So let's see how far over here on the board I'm going. Go right here. That looks great. And then on this side, I can go to about here. Okay, we got a whole big board. All right, so what we're going to talk about in chapter 9 is where we go into the book, section 9.1. We're going to investigate the idea of what's called a group, okay, a mathematical group. So this is related to the idea of a mathematical system. So that's the first heading on the page that I've given you. And so our first blanks are this: mathematical system consists of a set of elements that can either be as large or as small as you can think of, and at least one, what's called a binary operation. I'm going to define that for you in a minute. So that's the definition of what a mathematical system is. A group is a specific type of mathematical system. That's why we start there. We're starting something very general. We're going to go specific. A binary operation, you are all familiar with this. You've taken arithmetic. A binary operation is simply a rule that can be performed on any two elements of the set. I'll give you a moment to catch up with that. So under that, I've just given us some examples of mathematical systems. You're going to see these. My main purpose in these examples is I just want to remind us of some of these sets and what they are. Okay, use some words, some names. I want to make sure that you are comfortable with them. So the first example on the page, example 1, this is a mathematical system, addition of whole numbers. Okay, when you were in elementary school, that's where you started, was addition of whole numbers. I don't know if your elementary school teacher taught you that it was a group in a mathematical system, anything like that. Okay, so just want to remind you, the whole purpose of this is what are the whole numbers? Okay, you might not have ever known, or maybe it's been a while. So the whole numbers are this set. So when you, in this first section, we're going to talk about all of these large sets of numbers. When we come back and we talk about section 9.2 next time, we're going to talk about small sets of numbers or letters or whatever else and determine if they are groups or not. The whole numbers is this set of numbers. It's the set of numbers that starts with 0 and then it counts by ones up forever. Okay, so 1, 2, 3, 4, and at some point you get tired of listing the numbers. So what math people do is they put 3 dots in a row. I don't assume in this class that you've taken MGF 1106. If you have, then you remember in MGF 1106, maybe some things about sets, because that's the very first unit there. If you had me, then I told you that these three dots, this is called an ellipsis. And all an ellipsis tells you to do is just keep following that pattern, okay, so that I don't have to keep writing it down. So 6, 7, 8, 9, 10, forever and ever and ever, those are the whole numbers. So if I define the set of numbers, the whole numbers, and then the binary operation is addition, what I have created is called a mathematical system. Okay, and what we're going to do is we're going to determine as we go through this section is we're going to look at the characteristics of what makes a mathematical system this special kind of thing called a group, okay, which we'll then get to have fun with once we know what those are. The second mathematical system that I defined for you right there in example 2 is the multiplication of the rational numbers. So example 2 is multiplication now the rational numbers are a little more difficult to write as a set because you can't particularly list them. So what I'm going to first do is I'm just going to list some examples of rational numbers. Anything that you can write as a fraction is a rational number. So a half, that's a rational number. 5, because you can write 5 as 5 over 1. That's a rational number. -3/4, 10/7. And I could go on and on all day because the set of rational numbers is an infinite set and it's very large. Again, I don't assume you've taken MGF 1106. If you have, then maybe this will look a little bit familiar. The way you would write the rational numbers as a set is you would use what's called set builder notation. And the way you would do that is this. You'd say, okay, the rational numbers are the set of numbers that can be written in this format. Okay, it's the set of fractions. So it's the set of numbers that can be written as A over B, as a fraction. So it's the set of numbers that can be written as A over B such that, and here are the following conditions. A and B are integers. I'm going to define that set next in case you don't remember what an integer is. This symbol right here looks like an E with the corners shaved off. That means is an element of. Okay. Maybe you have some MGF 1106 memories flooding back to you, and if not, this symbol means element of. There's one other attribute of the rational numbers that I want you to help me to remember because it's going to play a part in some of the questions we talk about. What can the denominator of a fraction never be? 0. Can't divide by 0. It's undefined. Okay, so we would let people know that A and B can be any integer at all that you can think of, with one exception: B cannot be 0. So that's the set of rational numbers. The other thing I wanted to mention about rational numbers is I know we hate fractions. We just hate them. And I just want to remind us real quick on how to multiply fractions. So for instance, if I have 3 over 4 and I want to multiply by 5 over 7, does anyone remember how you multiply fractions? Straight across. Yeah, no common denominator, that's adding. Okay, we'll talk about that a little later. Okay, but you just go straight across the tops, straight across the bottoms. Multiplication is usually the operation with fractions we can tolerate the most because it's just going straight across. So in the numerator, 3 times 5 is 15. In the denominator, 4 times 7 is 28. And there we go, 15 over 28. That's how you multiply fractions. One more example of a mathematical system. Okay, so we had the whole numbers with addition. We had the rational numbers, meaning the fractions, with multiplication. And then the last example I have, and there's lots and lots of examples. I'm trying not to bore you more than I probably already have. The third example is, again, I've just picked these because I just wanted to introduce these sets. Subtraction of the integers. This is a mathematical system as well. because it defines a set of numbers and it defines a rule, subtraction. And again, I just want to remind you what the integers are. The integers are related to the whole numbers, except the thing about the integers is not only do they go forever in the positive direction, they also go forever in the negative direction. So here are the whole numbers that we already talked about that form the right part of the set. The left part of the set, now we go backwards, -1, -2, -3, -4, ellipsis. They go backwards forever. So that is an example of a mathematical system. Okay, so just defining our terms so far. Any questions yet at all? Okay, well, what we're going to do now is we're going to now define, maybe some of this is reminder from some sort of high school algebra memory that you have. Well, we're going to define the 5 properties that make up a group, okay, when we're looking at this specific type of thing. And so again, I'm not assuming you know a whole lot about this, if anything at all. The next thing on your sheet is what's called the commutative properties. Does anyone remember? I mean, if you don't, it's fine. Does anyone remember what the commutative property says? In particular, you can do the commutative property with addition. What does the word commute mean? When you commute somewhere, what does it mean you're doing? You're going to work, you're moving. Okay, so the commutative property talks about movement of the things that you are doing the operation on. And there's 2 properties that we're going to deal with in this section that obey the commutative property. First, the commutative property says if you add A and B, then that is the same thing as B plus A. The order doesn't matter that you add things. So that's good. When you go to the grocery store, you don't have to worry about whether you check out your milk before your lettuce or the lettuce before the milk. It's going to add up the same way either way. It'd be inconvenient if it didn't. There's one other operation that is commutative. The order doesn't matter. Does anyone have a hypothesis? What's the other one? Yeah. Sure, multiplication. Perfect. So A times B, I'm going to use a dot for multiplication. You can use an X if you feel like it, is the same thing as B times A. We do not enjoy the commutative property with division or subtraction. I could show you with a quick example. Okay, so subtraction is not commutative. What's 3 minus 1? 2. What's 1 minus 3? Okay, these are not equal. So subtraction is not a commutative property. And the same thing would be for division. If I could give a quick example of that too, or you could trust me, one of those 2 things. That's the commutative property. The other property that you might have some familiarity with is the associative property. Okay, so the associative property says, okay, we've already dealt with order. What about grouping? Okay, so if you remember your arithmetic skills, when you look at an arithmetic problem, your eye is always drawn to the parentheses. So you start there. So associative property has to deal with grouping. And here's what it says. Okay, the associative property in particular says for addition that if I have A plus B in parentheses, and I would start there with my arithmetic, and then I have the plus C outside, as long as everything is addition, then what I can do is I can keep the order of those 3 things the same, but I can change the grouping. So I can start with the B plus C and then add A later. Notice I've not changed the order. A plus B plus C, A plus B plus C. What I've changed is the grouping. I've changed where you would start the problem. So the associative property. This allows us to come up with clever ways to add numbers quickly, if you have a list, you pick out things that add up to 10, because it doesn't matter what order you add things in. And the same thing, again, is true for multiplication. If you have A times B times C, then it's the same thing as putting the A outside and the B times C. Once again, the division and subtraction are not associative, so we cannot do a grouping thing. And you can make up virtually any example that you can think of grouping subtraction or grouping division would not work out to be equal. So I asked a quick question in example 4. We've kind of already addressed this, but I just want to formally make sure we do, because this is part of the problems. Now, as far as the associative property, I'm going to let you, well, we'll talk about that a little later. I'm just getting too excited about moving forward. So as far as commutative and associative, what operations with the integers are commutative and associative? I've already mentioned in the examples, but when if you want to write something down for example 4, you would say that addition and multiplication are commutative and associative. All right, once you've caught up, we're going to flip to the second page of this. Now, you may or may not have seen, or maybe that's triggering some neuron to fire in your brain, and you at least maybe remember those words, commutative and associative. The next 3, I am not assuming that you have really any familiarity with. And whether or not you're familiar with the other ones, it's not going to affect your experience. So the next one is called the closure property. The closure property says this: if a binary operation is performed on any 2 elements of a set, and the result is another element of the set, then the set is closed under the operation. So I'm going to write this down. So it's going to take me a minute, so it's not that super interesting. And then we're going to do some examples, because I know that this is kind of a goofy little definition. So if a binary operation, which I'm going to abbreviate as BO, is performed on any 2 elements of the set, and the result is another element of the set, and I think that's the blank, and the set is closed under the operation. I'll give you a minute to fill in those blanks. Then we're going to do a couple of examples, because I know that closure can be a goofy little operation or goofy little property here. And I want to make sure that you see this, because it's going to be important to your future for the next couple sections. I think this unit has 4 sections in it, so at least for 4 sections, this is going to have impact for you. So then I go to example 5, and I ask, are the whole numbers closed under addition? So back on your sheet, you can see what the set of closed numbers, or you can see what the set of whole numbers are. And so the question is, are the whole numbers closed under addition? So what this question means is, if I pick any 2 whole numbers, do I always get a whole number? Yeah. Well, let's pick some examples and see. And we're not going to prove this, but we're going to be able to demonstrate whether this is true or whether this is not true. So somebody give me a whole number. 26, and then I heard a 1. What's 26 plus 1? Is 27 a whole number? Yes, it is. Okay, let's try again. Let's say that I have 100 plus 42. 100 plus 42 is 42. I'm never going to have a situation where I get a decimal or a fraction when I add two whole numbers together. So the question, are the whole numbers closed under addition? And the answer is going to be yes. Any two whole numbers I pick, when I add them, I get another whole number. So if you need a summary statement, because I understand this can be hard to digest, the summary statement would be any two whole numbers I pick, when I add them, give me another whole number. That's what it means to be closed. I'll give you a minute to write all that down. Then I'd like you to make a hypothesis. We'll do this together in a minute, but I'm going to give you 60 seconds to think about it. Maybe try a couple of examples. Example 6 says, are the whole numbers, which we just talked about being closed under addition, are the whole numbers closed under subtraction? And so take a minute, think about it, make a hypothesis. If you're wrong, that's okay. We're learning, and that's why we're here. So there's nothing to get upset or freak out about here. So remind me, from the first page, what are the whole numbers? What number do the whole numbers start with? 0, and then they count up, right? 1, 2, 3, 4, 5. So give me a hypothesis, give me a guess, and then we'll do some examples. Do you think if I take any two whole numbers and I subtract them, do I always get a whole number? No. Okay, I'm hearing a lot of no's. Okay, so that's the hypothesis. Will somebody give me an example that demonstrates that this is a no? 1 minus 100. 1 minus 100. 1 is a whole number. 100 is a whole number. That fouled the ellipsis. What's 1 minus 100? Are negative numbers whole numbers? Okay, so this right here is not a whole number. And that's why it's not closed, because I can do this operation and I can get things outside of the set that I was considering. One more example. Again, I'm going to give you a minute to think about this, make a hypothesis for yourself. So example 7 says, are the integers closed under subtraction? All right, what's your hypothesis? Are the integers closed? Do you always get another integer when you subtract? Yes or no? Yes. Let's pick some examples and see. Okay, so I agree with you. That's a good hypothesis, but let's just verify. So first off, if you do 9 minus 7, 9 is an integer, 7 is an integer, that's 2, another integer. Let's flip it around. Let's see if I get an integer when I flip. So 7 minus 9. 7 minus 9 is -2. Is -2 an integer? Yes, it is. Let me just try a couple more. If I have -2 minus 6, maybe you need your calculator for this. -2 minus 6 is -8. That's an integer. So it looks like no matter what two integers I pick from that large set, when I subtract, I'm always going to get an integer. And that is indeed true. So that is a closed set. Are you getting a little more of an inkling of what it means for something to be closed? Okay, I know this is difficult. This is higher level stuff. So don't be shy. Don't be afraid to ask any questions. if you have them. There's lots of questions that you probably should have. Okay, so we have talked about 3 things so far. We talked about the commutative property, and I have told you that for these large sets, that addition and multiplication are commutative. You can take that to the bank, okay? You know that now. Associative deals with grouping. Again, I've told you addition and multiplication are associative. Take it to the bank. Closure, we've looked at closure and we said, okay, addition or subtraction, any of them can be closed. It just depends on what set you're using. So here's the fourth of the 5 things we're going to talk about, and then we're going to get to the whole purpose of being in this set. The next one's called an identity. I got to spell it right. There we go. That's better. Identity. I am not a good speller. So, given an element of a set. So if I give you an element of the set, an identity, and that's the first blank. An identity is an element that produces a given element in the binary operation. That's the other blank, in case you're following along. When the binary operation is performed. Okay, that is a lovely definition, but maybe that provides more confusion than enlightenment. So I'm going to show you the example. I'm going to show you the identities that we know we have. Okay, so example 8 says, what's the identity for integers if I'm adding? Okay, so example 8. Okay, so what's the identity for integers when adding? So for instance, what that means is if I start off with the number 9, plus what is going to give me 9? So given an element of the set, 9, the identity is the element that I'm pointing at that produces the given element, 9 again. So what do you add to anything to keep it the same thing? 0. There you go. 0 is the identity for addition. What this is labeled, you don't have to remember this word. I can barely spell it, okay? But 0 is what's called the additive identity. Additive identity. We're spoiling the surprise. I'll let you shout it out in a minute. I love your enthusiasm and excitement. Okay, example 9. I'm going to give you 60 seconds. It says, what is the identity for integers under multiplication? So just take a moment and make a hypothesis. What element will always produce the given element when you multiply? Okay, so again, I'm starting off with an integer. Let's say 9 again, because I'm really creative. This time I'm multiplying by something. What is the identity going to be here? It's going to be 1. Yes, when you multiply by 1, you get the same thing. So again, you don't need to know the terminology. I'm just happy to know these words. This is called the multiplicative identity. So now you know the identities. When you add, the identity is 0. When you multiply, the identity is 1. Okay, so just trying to take you through for these large sets, these integers, the whole numbers, the rational numbers, just trying to give you this because these are going to affect the answers to the 10 or so homework problems that you have to do tonight. There is one more property. Okay, so we've done the commutative property, we've done the associative, we've done the closure, we just did the identity. There is one more called the inverse property, or the inverse element. Okay, so for inverse, two elements. Okay, so you need two elements. You pick two elements out of your set. Two elements in a set are called inverses if the binary operation is performed and the result is the identity. I don't know why I left two blanks there. I must have just been enjoying using the space bar a little bit. So for instance, example 10. The question is, does every integer have an inverse under multiplication? And then we'll do the same question, and I'll just erase the word multiplication, and we'll say, does every integer have an inverse under addition? So does every integer have an inverse under multiplication? Okay, well, let's say this. So if I multiply, so here's an integer, 2. We just answered this question. Okay, so it's right there on the previous page. What's the identity? Because the definition says I'm going to pick two elements and I am going to get the identity. What's the identity when I multiply? 1. Okay, 1. So here's the question. Forget that we're talking about integers for just a minute. If you remember your arithmetic, 2 times what number is going to give me 1? Half. Half of 2. Half of 2 is 1. Okay, your calculator can tell you that. I know it's probably been a long time since arithmetic for any of us, so I'm just reminding you that this is called the reciprocal. Okay, so in arithmetic, the inverse when you multiply is called the reciprocal. Well, here's the problem. Does every integer have an inverse under multiplication? Is a half an integer? No, it's not. It's a rational number. So here's how we would answer this question. Does every integer have an inverse under multiplication? No, it doesn't. There's no integer that is your inverse under multiplication. Now you might say, hey, Perkster, that's crazy. I can see the inverse right there. You wrote it. Okay, I'd have to change one word of this to be able to say yes. Instead of using the word integer here, I would use the word rational numbers. Then you can say, yes, my rational numbers do have reciprocals. With one exception, we'll get to there. Okay, but in general, that's what we've got. So the reason I say no on this is because the inverse is no longer an integer. It takes me out of my set, so I don't care about it anymore. So with that said, I told you we were going to ask the same question, but this time we're going to change it to addition. So example 11 says this. Does every integer, again, have an inverse under addition? Okay, great question. Well, here we go. So what's the identity for addition? So here we go. What would the inverse of 5 be? 5 plus what would give me 0? Are both of these things integers? Now let's try one more example. Let's say I have negative 11. Negative 11 plus what is equal to 0? 11. Are both of these things integers? Yes. So because both of these things are integers and I get the identity, the answer to this is yes. Just want you to, I understand this is goofy stuff. This is as high level as we're getting in here. We just basically, if you were in a college class that was going to go into group theory, basically this is page 1 of the group theory book, okay, that we've just done. Okay, that's all we need to do. So these things. So just want you to be aware of this. Be careful that you understand what set we're talking about. That's why I went and I reviewed those sets earlier. Okay, because if I changed this to the whole numbers, well, the whole numbers no longer have inverses under addition because 5 plus negative 5 is 0. Negative 5 is that a whole number? Negative 5 a whole number. Where do the whole numbers start? 0. So negative 5 is not a whole number. So the answer would be different. You got to be careful. So it's just those little details that you got to be careful of. Now, here's the even better news for you. This first section, 9.1, today's topic, the homework they're going to have, this is the only section that deals with these really big sets, the whole numbers, the integers, the rational numbers. When we come back and we continue this discussion on groups, we're just going to talk about small sets of numbers that we can write as a table. It's going to be a lot more fun. Okay, but we had to define our terms today so we could have that fun when we come back on Wednesday. All right, so here is now the whole reason why we talked about these 5 things. At long last, we can now define what the whole title of the section was, and that is what a group is. So the properties of a group, a mathematical system that meets the following 4 requirements is called a group. Okay, I'm going to let you fill in that blank. I'm just going to write properties of a group. So that first blank is just the word group. A mathematical system that meets the following 4 properties is called a group. And the properties are just the things that we've already talked about. So here we go. The first thing. So if I ask you, and I will, this is what your homework's going to be. And we're going to do 3 problems that are just like your homework. Okay. And then when we come back, we're going to do more problems, just with easier to work with sets. The first thing you look for is, the first thing a group has to be is has to be closed. So the first property of the group that you look for is it closed? If you're doing a problem and you notice that it's not closed, you're done. It's not a group. You don't have to go through the rest. Okay, so I'm giving you these in the order that for something to be closed, for the next thing to be true, it has to be closed. Okay, so they build on each other. So that's why when you check things, check in this order. Because if it's not closed, then you don't have to go any further. It's probably not any of the other things either. The second thing is that an identity exists. The third thing is every element has an inverse. It's just the things that we talked about. We're just kind of formalizing them, gluing them together to make something bigger. So the properties of a group, it's first closed, Then you'll identify the identity. If it doesn't have an identity, then you're done. It's not a group. Third thing, every element has an inverse. If there is any element at all that does not have an inverse, you're done. It's not a group. And then the last thing, the fourth thing, is that it's associative. Well, you already know right now that it's addition and multiplication are the only things that are associative. So if you're right away, if you're given something with subtraction or division, then you are done. It's not a group. Underneath that, there is a specific type of group that satisfies the commutative property. And so you can have a specific type of group and it's called, very cleverly, because math people are super clever in the way they label things, it's called a commutative group. So a commutative group satisfies these four properties, and then it has a fifth property, it's commutative. And again, we know addition and multiplication are commutative. If it's not multiplication or division, or excuse me, multiplication or addition, if it's division or subtraction, then it's not commutative. It's not a commutative group. Okay, so all that to say is these last three problems we're going to do with the remainder of our time, these are examples of, there's like 10 homework problems. I can't get into too much depth here with you because this is pretty advanced, pretty fast kind of math. I'm going to put one of these on your next test. Okay, it's going to be the very first problem. The reason I'm putting this on there is I just want to make sure you know what the properties of a group are. So what we do in these next three problems, this process, I'm going to ask you to do one of these on the next test. Okay, there's 10 homework problems. You got a quick little quiz. So hopefully you remember. Okay, so the next example, example 12, says this. Determine if the mathematical system consisting of whole numbers with addition. So whole numbers with addition, I want to know, is this a group? Okay, is this a group or is this something that I'm not interested in as a group? Okay, well, here goes. Number one. On your list, you're just reading from the list. I'm asking you to do this just to hopefully build a little muscle memory in your brain. What is the first thing, if it's going to be a group? It has to be what? Closed. Okay, so here's the question. Is it closed? I'm going to write the word closed. I'm going to put a question mark. Well, we did this earlier. When I add any two whole numbers, do I get a whole number? Yes. So all I'm going to ask you to do is just give me an example. Either an example that says why it's closed or an example that shows me it's not. Okay, so one of those. And we've gone through that. We've done this already. Okay, so it's nothing new. Okay, but I know it's hard. So that's why we're practicing. So is it closed? The answer is yes. And here's a quick example. 10 plus 2 equals 12. Yes, I picked two whole numbers. I got another whole number. That's always going to happen. It's closed. And if you need to make yourself a little note, the note would be to go back to example 5. Example 5 is where we talked about that in a little more detail. The whole numbers being closed under addition. What's the second thing that makes it a group? What's from the list that I just gave you a moment ago? There's an identity. So I want to know, is there an identity under addition? Well, what's the additive identity? We talked about that. It is 0. Is 0 a whole number? Yes, it is. So is there an identity? Yes. And the identity is 0. So again, just give me a quick example, just to show me that you know, okay, that the identity is 0. Or you can just say, in fact, even better, just say the identity is 0. Boom. What's the third thing from your list? There's an inverse. Every element has an inverse. Do inverses exist? No. Who said no? Why not? That is well said. So here's an example. In fact, we did this in a previous example. Okay, but just exactly what was said is perfect. That if you start with any whole number like 8, well, the inverse is going to be -8. Well, here's the problem. This is not a whole number. That's not a whole number. That's why inverses don't exist. We are talking about whole numbers. We're not talking about integers here. So because that's not a whole number, inverses don't exist. Fails. You don't even have to do the fourth one. You don't have to talk about associative. Okay, and then if we wanted to know if it was a commutative group, you wouldn't have to do step 5. We're done here. Is this a group? Then the answer is this is not a group. It doesn't meet all the criteria. It's all or nothing as far as being a group is concerned. So here is what I would like you to do. We will come back to 13, and we'll do that one together. 14 is very similar to what we just did in difficulty level. So I'm going to give you 2 or 3 or 4 minutes to think about, is the set of integers under addition a commutative group? So it has that 5th characteristic too. So give it a try, do your best. You don't get it all or you don't get much of it, that's okay, we're learning. Okay, step one. Is this closed? Well, we talked about this earlier. Okay, so here's an example, meaning if I pick any two integers and I add them, do I get another integer? So if I take -7 plus 4, -7 plus 4 is -3. Is that an integer? Yes, I'm never going to get anything. I'm never going to get any fractions. I'm never going to get any decimals if I add. Okay, so is this closed? Yes. And you might say something like, you always get an integer when you add two integers. But you don't have to say that. An example suffices for me. Either an example demonstrating, or an example that demonstrates it's not. Second thing is there an identity? Well, what's the identity for addition? 0. Is 0 an integer? Yes. Okay, the identity is 0. Perfect. Yes, so yes. Is there an identity? Let me squeeze the word yes in there. The identity is 0. 3. Third thing, does everything have an inverse? Okay, so for instance, if I have -7, what's the inverse of -7 going to be? 7. If I have 11, what's the inverse of 11 going to be? So does everything have an inverse? Yeah, it's called the opposite. If you remember your arithmetic, if you don't, that's fine. But yes, do inverses exist? Yes, everything has an inverse. The fourth thing, associative. I told you could take this one to the bank. This is from page 1. Is addition associative? That's wonderful. And now at this point, you have a group. Okay, so integers under addition are a group, so that's good. But just because something's a group doesn't mean it has to be commutative. So we've got that last thing. So this is number 5. Number 5 is, we're only asking this because we've asked about this specifically. Is it a commutative group? So is this commutative? Is addition commutative? Yes. So the integers under addition, are they a commutative group? The answer is yes. So one more example, and then I'm done spraining your brain for the day. Yes. Oh, so I don't want you to answer. I mean, I understand that example would suffice for both, but I don't want you to use that for both because, again, the order matters. Each of these builds on the other. So if you get to something that's closed, the identity, nothing else matters if it doesn't pass this. Okay, so you can have an operation that's commutative, but then maybe the identity doesn't exist for something. Okay, so just make sure to keep that in mind, that the order is important here. But as long as you say it out, you could say, okay, you can see my example over here. That's fine. Okay, one more example, and then we are done for the day. So good job. This, in my mind, is one of the hardest sections all semester. So I understand if you're feeling a little topsy-turvy. If you're feeling good, then you can feel good about the rest of the semester too. All right, so here we go. Example 13. Just wanted to give a slightly different set just to make sure I've covered everything that you're possibly going to see in your homework. So example 13 says, determine whether the positive rational numbers under multiplication. Okay, I'm only asking if it's a group. I'm not asking if it is a commutative group. Okay, not interested in the commutative part of this. The reason I wanted to mention this is a couple of the problems, in order to make them a little more interesting, deal with the idea of just limiting the rational numbers to either being positive or negative. What it means when it's positive means it is bigger than 0. Okay, that's positive. Not equal to 0. That's important because 0 doesn't have a reciprocal. You can't divide by 0, so then you won't have an inverse. That's why this problem is saying let's only deal with the positive ones so that we can have reciprocals. Okay, so whenever you see the word positive in one of these problems, know that it's just talking about numbers that are strictly bigger than 0. Okay, 0 is not a consideration. So then, knowing that, since I've defined that, I'm going to give you 2 or 3 minutes. Go ahead and go through the 4 steps. This is not commutative group, so I don't care about commutative. Go through the 4 steps. Determine your hypothesis if you think this is a group or not. So first thing, we've got our positive rational numbers, meaning any positive fraction, and we're multiplying. Is this closed? So this means if I take any 2 fractions and multiply them, do I get a fraction? So for instance, let's just use an example to see if this is yes or no. If I do 3/4 times 9/2, those are both fractions. When I multiply them, I get 27/8. Is that still a fraction? Yes. Is it still positive? Yes. So I can't think of any 2 fractions that I would multiply and I would not get a fraction. Okay, so is it closed? Yes. When you multiply 2 positive fractions, you always get a positive fraction. Did anyone answer no to that? We need to talk about it. Identity. Well, what's the identity under multiplication? 1. Can I write 1 as a fraction? 1/1 or 5/5? Yes. So does the identity exist? Yes. The identity is 1. And I'm just going to write in parentheses that 1 is, or 1 can be written as a positive fraction, i.e. 1/1 or 5/5 or anything else. Inverse. So does every positive fraction have something I can multiply it by that gives me 1? So for instance, if I start with 5/4, what would I multiply 5/4 by to get 1? The reciprocal. Is the reciprocal a positive fraction? Yes, it is. And you could do that for any fraction. Okay, the reciprocal is what you multiply by to get 1. And so the reciprocal, this is a positive fraction. So inverses exist. Okay, last but not least, is it associative? Well, I told you could take this to the bank. Is multiplication associative? Yes, it is. Okay, multiplication is associative. So are the positive rational numbers under multiplication a group? The answer is yes, they are a group. Boom.